Greetings and welcome to what this book calls analytic geometry. But we're going to be calling it just conic sections. We're going to be diving deep into some different cross sections from cones. You've already had some exposure in the past in like in the intermediate algebra, college algebra type courses with circles and with parabolas, but you were limited to parabolas that were like cupped up or cupped down, so with a vertical axis of symmetry. So we're going to expand that today, specifically in this video, into the parabolas that face left and face right with a horizontal axis of symmetry. And then eventually we're going to cover some of the other conic sections. Now, just a really quick kind of summary. You've seen this image. If you've watched any of my college algebra videos, you've seen this image before. But when we're thinking about conic sections, we're thinking about a cone that looks like this. It actually looks like two ice cream cones where the points are glued together. And when we're looking at the conic sections, we're trying to look at, like, if a plane cut parts off. Like if you drew a plane that sliced right through it down here, like parallel to your circular base, you would end up, the cross section would be a circle. So that's what that cross section would look like. Or if you had a plane that intersected at an angle instead of parallel to your circular base, at an angle but still cutting nicely through, you would end up with an ellipse. So you've talked about circles before in college algebra. We're going to add ellipses in this unit. We're going to talk about those. Those are fun. I like ellipses. And if you just cut through one part of the cone, but not like not parallel to your circle or at a slight angle like the ellipse, but rather cut through like part of the cone including your circular base, the cross section from that ends up being a parabola. And if you took a plane and decided to cut, like hold the plane vertically and cut straight through, not through where the cones touch, but straight through elsewhere, then you end up with something called a hyperbola. And we're going to get into those too. So we're going to cover all kinds of different things. We're going to look at parabolas that face left and right. We're going to look at ellipses, and we're going to look at hyperbolas. And then you should already be pretty well versed on circles. So that's what we're getting into. Okay, so let's do a quick little recap of parabolas. The ones you've already learned about have that format of y equals a times x minus h squared plus k, where hk is the vertex. And you know that if a is positive, the parabola holds water. If a is negative, the parabola dumps out water. So you're already familiar with that. X equals h is the axis of symmetry. And that's pretty much what you've covered with those. So if you had something like let's say you have a parabola that's like this, then you know its vertex, it would be at -2, 1. And then the axis of symmetry is that invisible line that goes through that vertex. That would be at x equals -2. That line, equation that line's x equals -2. So you know, if you folded the graph paper along that line, you know that the two sides of the parabola would match up with each other. They're nice mirror reflections across that line. So you're already familiar with those. And then you know too that since it's holding water like a cup, you know that the A had to be positive. If A were negative, then it would be upside down. But we're going to take this today and expand, and we're going to take the y minus k equals a times x minus h squared, and we're going to interchange the y minus k and the x minus h. So it looks like this. And when we do that, we're going to end up with parabolas that either face to the right or face to the left for those equations. So you're going to have a horizontal axis of symmetry. Thankfully, HK is still the vertex. So that's still nice and workable there. We don't have to really do anything different for that. Now this will not be a graph of a function, because if it's facing left or right, it will not pass the vertical line test. So this is a relation but not a function, this type of parabola. If A is greater than 0, if it's positive, then you know that it opens to the right. If A is less than 0 or negative, then you know it opens to the left. So the A, now instead of holding water or dumping water, you can talk about it facing to the right, facing to the left, opening to the right, opening to the left. Okay, so let's look at graphing one of these, and let's give the domain and range. Let's say that you have x minus 4 equals negative y plus 2 squared. Okay, so as soon as you see the squaring happening with the y, you know you've got that situation where it's going to open to the left or open to the right. So my vertex is still hk, so it's going to be 4, -2. My a is -1, which tells me that the parabola is going to open to the left. And then I can go from there. Let's see what kinds of... Let me bring this down a little so I can start working on drawing it. Okay, so for -2, I'm just going to let each grid line represent 1. For -2 would be right here. That's my vertex. And I know which way it's cupped. I know it's going to open to the left, like that. And then just like graphing those other kinds of parabolas, it can be helpful to do maybe a little XY table, come up with some values. Like if I were to plug in, let's say I plugged in 0 for x. I expect when I plug in 0 for x to actually get 2 y values back. Plug in 0 for x, I get -4 equals negative y plus 2 squared. So y plus 2 is going to equal plus or minus 2, because square root of 4. So y would be either 0 or -4. So we have 0, 0, and we have 0, -4. So that's 2 more points. And if you want more points than that, you can do more. Like, let's say you let x be 3. You'd have -1 equals -y plus 2 squared. So y plus 2 equals plus or minus 1. So y would equal either -1 or -3. So at 3, it would be at -1 or -3. So that's enough points. So now you can connect the dots with that nice little parabola. In this parabola, the domain, how far left, how far right, or what x values are included. Well, this thing extends infinitely to the left, so that's -infinity. And then when you go to the right, it stops at the vertex, which is at x value of 4. We'll use a bracket because it includes that 4. For the range, that's the y values, how far down, how far up. These little arrows indicate that it's going to extend forever down and to the left, and also up and to the left. So down and up, -infinity to infinity. So that's the range. All right, so that's basically what's happening when you have your parabolas facing left and right. So the x and y situations got swapped out, and then you get that new format. Now, you're not always going to be given in that nice form. Sometimes you have to take them and work the equation out to get it in a form that's more usable. That's where you're completing the square can come in. Let's say they ask you to graph something like x equals 1/2 y squared minus 4y plus 6. So let's say you have to do that. We want it in that x minus h equals a times y minus k squared kind of format, because that makes things a lot easier. So I'm going to go ahead and subtract 6 from both sides. Get the y's by themselves on one side. Then I'm going to factor out that 1/2 from the y's. And this is where I end up so far. I'm going to complete the square on this y squared minus 8y. So I have to do 1/2 of 8 and then square it. So I have x minus 6 equals 1/2 parentheses y squared minus 8y. So I'm going to add 16 here. But the thing is, I can't just randomly add a 16 into the equation. The equation already has an equal sign. So the two sides are already equal. If I add a 16 in right there and inside those parentheses, that now makes it lopsided. So I got to balance that out. Technically, I added 1/2 of 16 because I have that 1/2 outside the parentheses over here. So technically, I added 8. So I need to balance it out by subtracting 8 on the same side. Or if you'd rather, you could think about it as adding 8 over on the other side if you want to keep it balanced that way. I like to think about it that way. Like, what did I add on one side? Let me go ahead and add it to the other side too. Just keep everything balanced out. So I end up with x plus 2 equals 1/2. And I completed the square. So I ended up with a perfect square trinomial that factors into y minus 4 quantity squared. And now I've got that lovely form that I need. In that lovely form, I can see my vertex is -2, 4. I can see that my a is 1/2, which is greater than 0. And since the y is squared, I know then that this means it's going to face to the right, like that. Okay. Let's see. So I can plot my vertex. -2, 1, 2, 3, 4. You know what? I'm looking at that. I think I need to move it down a little ways more. Let me draw that a little differently. I need that to be 8 up there. 8, 7, 6, 5, 4, 3, 2, 1, 0 right there. It's going to be 6 there. That's 8. That's 4. Okay. So -2, 4 is going to go right here. I know since it's going to open to the right, I know that I have an axis of symmetry going right through that vertex, and it's going to be horizontal. It's going to be at y = 4. I can do a little XY table to get some extra points. If I use, let's say I use 0 for x. 0, so 2 = 1/2, so 4 = y - 4 squared, plus or minus 2 = y - 4. So then I get either 6 or 2. So 0, 6, and 0, 2. Now, notice that with the axis of symmetry, like if you get 1 point, like, okay, so for the 0, 6, we see that it's 2 spaces up from our axis of symmetry. So then the other point has to be 2 spaces down from the axis of symmetry. And that's where we have the 0, 2. Let's say I plug in 6. Okay, I plug in 6, I get 8. 2 times 8 is 16. Square roots plus or minus 4. So 4 plus 4 is 8. So I know 6, 8 is one of my points. But then I know with the axis of symmetry situation, 8, that point is 1, 2, 3, 4 above my axis. So I got to go 1, 2, 3, 4 below my axis. And my other point is going to be at 6, 0. Or I could plug 6 in, and or I could finish solving by plugging 6 in and seeing what I get. But just notice that there's equal spacing on either side of that axis of symmetry between those points. So that could be like a little shortcut in a way. And for this question, the domain, well, the x values start at -2 with that vertex. And then this graph shoots off to the right forever. So the domain is -2 to infinity. And then for the range, this graph goes forever down and forever up. Nice and smooth, no gaps or overlaps. So -infinity to infinity. And once again, this is not a function because it fails the vertical line test. But it can still, it's a relation. It's a set of ordered pairs. So it can still have a domain and range. Kind of a cool little thing to think about when you're dealing with these kinds of parabolas. You're not like with those sideways one, they're not functions, so you don't have inverse functions. But watch what happens when you work with these. Like, let's say we start with y = x squared. Y = x squared would look like this. Just doing a real quick sketch with a few points. I'm not going to do a whole bunch of points. Y = x squared. And then let's switch it up. Let's use maybe green for x equals y squared. If I do that, still have 0, 0. But this time, it's going to look like this. So even though you can't call them inverse functions, like the original y equals x squared, it's a function, but it's not, it passes a vertical line test, but it's not one-to-one. It fails the horizontal line test. So as is, with the full domain, you can't, it doesn't have an inverse. Now you can restrict the domain, but we're not doing that right now. But the x equals y squared is not the inverse, but still, if you draw the line through y equals x, still have that cool effect where the two graphs are reflections of each other across that line. Yeah, I didn't draw it nicely enough right there, but you still, yeah, you've got that reflection. So kind of a cool thing to notice. Okay. So continuing on, we're still going to be talking about parabolas. But now I'm going to introduce something that you've either never heard of or haven't heard of in a while. I know a lot of times in high school classes they talk about these things, but like in our college algebra class we don't really talk about these. We're going to talk about something called the focus and something called the directrix. Let's say you have a parabola. I'm just going to sketch one real quickly here. It's just kind of a generic parabola. I'm just going to have this one centered at the vertex at the origin. This one holds water. For this particular parabola, you still have that axis of symmetry. But what I want to talk about today are two other things. Now, for this particular parabola, I have no idea if these things are actually located in these spots. I'm just trying to tell you what these are. There's a point called the focus. And for this parabola, there's a horizontal line called the directrix. And I want to talk about what these are. A parabola, by definition, you've probably not heard this definition before, but a parabola is a set of points in a plane equidistant from a fixed point that's the focus, and a fixed line. That's the directrix. So you could pick any point you want on this parabola. And again, this is just a quick sketch, so it's not entirely accurate. In fact, in this particular parabola, this looks really bad. But you will know that the distance from any point on the parabola to the focus, and then that same parabola straight down to the directrix, will be the same. Sorry, not drawn accurately. It's just doing this for definitions purposes. So that's what your focus and your directrix are. You could take any point on the parabola. This is a set of points. It's equidistant from a fixed point and a fixed line. So you can take any point you want, and the distance from that point to the focus and that point to the directrix will be the same. All right, so let's develop some formulas for finding the focus and directrix. Okay, so let's redraw this little parabola here. Again, held it down too hard, so it thinks I was trying to draw a line there. Okay. So we're going to draw this again. Actually, maybe we should change colors to make this a little easier to think about as separate from the parabola. Okay. And we're going to talk about a point, some point, I think your book calls it P. Yep. So some point P on the parabola with coordinates x, comma, y. And then the focus has coordinates 0, comma, P. So this distance here is P. And then the distance here is also going to be absolute value of P. So then this line down here is y equals negative P. That's the equation of that line. And of course, we have the vertex at 0, 0. And then, and then we're going to look at a point here. That's going to be point D on the directrix, and it has coordinates x, comma, negative P. Because you got x there, and then down P units. All right. And yeah, don't forget the vertex at 0, 0. Okay. We know that the distance from point P to point F has to be the same. So the distance from point P to point F, so some point on the parabola to the focus, has to be the same as the distance from point P to point capital D there. So from some P on the parabola down to, straight down to a point on the directrix. So those two distances have to be the same. So our point P has coordinates x, comma, y. Point F has coordinates 0, comma, P. So if you want to do the distance between those, you'd have the square root of x minus 0 squared plus y minus P squared. And then for PD, again, P has the coordinates x, y, and then D has coordinates x, comma, negative P. So the distance there would be the square root of x minus x squared plus y minus negative P squared. So we've got square root of x squared plus y minus P squared. And that's going to equal the square root of y plus P squared, because x minus x is 0 in there. Square both sides, x squared plus y minus P squared. That squared should have been on the outside. Apologize for that. That erases that whole thing. And then that equals y plus p squared. So then we'll FOIL that, or multiply, combine like terms, that kind of thing. So we'll have x squared plus y squared minus 2yp plus p squared equals y squared plus 2yp plus p squared. Y squared and p squared are on both sides, so once you subtract them from both sides, they kind of go away. X squared minus 2yp equals 2yp. X squared equals 4yp. Or x squared equals 4py is another way to write it. That's what your book will write it. And now we can use that. Back up to that original parabola. The equation of that parabola is y equals ax squared, because it's centered at 0, 0. So, y minus 0 equals a times x minus 0 squared. So you end up with y equals ax squared. But now we have this little thing where x squared is the same thing as 4py. So y equals a times 4py. So 1 equals a times 4p. So a equals 1 over 4p. All right. That's important. A equals 1 over 4p. We got to keep that in mind, because that's going to help us if we're trying to find focus and directrix, especially if we know A. Remember, P is that distance from, like in this case, the parabolas get a vertex at 0, 0. So P is that distance from the vertex to the focus, or from the vertex straight down, that shortest distance down to the directrix. And if you flipped it over, it would still be the same kind of thinking. And if A is positive, still it holds water. If A is negative, it dumps out water. All those things come into play. All right. So x squared equals 4py. This parabola has a focus at 0, p. Directrix at y equals negative p. So just thinking about how to sketch these so you can see what they look like. So if you have a parabola that's like this, or you can have a parabola that's like this. Again, I'm just doing quick sketches here. I'm not doing this very accurately. For the first one, x squared equals 4py. Focus is at 0, p. Directrix is at y equals negative p. In this case, p is greater than 0. And then if you have the x squared equals 4py, where p is less than 0. So then your y equals negative p is up here. And then you got your focus, 0, p here. So both of those, your axis is at x equals 0. That's your axis there. All right. Now if you switch it up, you can do left and right also. Instead of x squared equals 4py, you can have y squared equals 4px. Still, focus has to do with that P. This time it's going to be at P0 instead of 0P. Directrix is going to be X equals negative P. So now you're going to have the directrix is going to be a vertical line instead of a horizontal. Horizontal axis of symmetry opens left or right. So if we sketch those situations, again, I'm sketching, so it's not going to be accurate. Okay. Oops. So you can have a focus at P comma 0, and you can have a directrix at X equals negative P. So this is y squared equals 4px when P is greater than 0. And then this one, you can have your focus still at P0, and your directrix, X equals negative P still. So for this one, it's for still y squared equals 4px, P less than 0. Okay, and then your axis of symmetry on that, remember, the axis of symmetry for that is going to be the y equals 0. Because it's centered on the origin. It still has the vertex on the origin for those. In a minute, we'll get to what happens if the vertex is not on the origin. It's not too far of a stretch. It's okay. So, what do we want to do next? Let's do an example. All right. Let's say they give us the equation x squared equals negative 4y. And they say give the focus, directrix, vertex, and axis of symmetry for this parabola. Then use the information to graph the parabola. Okay. So remember this parabola is already written in that form of x squared equals 4py. So 4p equals negative 4, so p is negative 1. So then we know that this type of parabola is going to go like this. So we have that negative p, or originally we had that negative 4 by the y. So that negative number is telling me, this is going to be one of those, the x is the squared, so it either had to hold water or dump out water. And since we have that negative in front of the y, the negative 4, and you end up with a negative p, it's going to dump out water. So that's the situation there. The vertex is at 0, 0. And the axis of symmetry is going to be a nice vertical line. So it's going to be at x equals 0. Okay, let's see. How many values do I need for this? That should be fine. Do it like this. Okay, so the actual parabola, if you want, you can always go, well, y equals negative 1/4 x squared. You can use that if you want for doing a little xy table just to get some points for the parabola. Let's use 2 and negative 2. So 2, negative 1, and negative 2, negative 1. And I think I used 4 and negative 4 also when I was doing this. Yeah, because I got negative 4 and negative 4. That's what I did. So it's kind of a little fat there as far as that parabola goes. Okay, but then I'm interested next in looking at my focus and my directrix. Now, if P is -1, then absolute value of P gives me that distance I need. So I can go 1 unit from the vertex down to get my focus at 0, -1. And I can go 1 unit up from the vertex to get my directrix. And that is at y = 1. And then I think it asks for the axis of symmetry too, which if you wanted to graph that, you can. That's, again, at x = 0. And there you have it. So focus is at 0, -1. Directrix is at y = 1. Vertex is at 0, 0. And axis of symmetry is at x = 0. So there's everything they wanted to know. You could pick any point you want to on this parabola. Any point, anywhere. And the distance from that point to the focus is going to be the same as that point straight, like perpendicular to the directrix. So those two distances are the same. All right, let's do another one. Of course, we just did one that was either cupped up or cupped down. Now let's do one that's either facing left or right. So this time the y is being squared instead of the x. So y squared equals 12x. Still know the vertex is 0, 0. All right. So we have that format, y squared equals 4px. So 4p must be equal to 12, which means p equals 3. Since that p is positive, that tells me that this thing is going to open to the right. Little xy table help me with some points. I already got 0, 0 from the vertex. I used 3 because 3 times 12 is 36, and the square root of that is both +6 and -6. And I felt like that was enough. I didn't really need much more than that. Okay, so 0, 0, +3, +6, +3, and -6. So there we go. This is a really stretch type. Okay, so that's the basic sketch of that graph. Now we still need to worry about focus and directrix. What exactly is going on there? Let me do this. 1, 2, 3. So if P is 3, then that tells me 3 to the right from the vertex is going to give me that focus. So 3, 0. It also tells me that 3 to the left of the vertex will give me that directrix. And this time it's going to be a vertical line. So the directrix is x equals -3. So we have our focus, our directrix, we have our vertex. This particular one, the axis of symmetry is along the axis here. So the axis of symmetry is y = 0. And I think that's it. I think that's everything we had to know. So again, You could pick any point you want on this parabola, and the distance from that point to the focus, and then that point perpendicular to the directrix would be the same distance. So those two distances would come out the same. That's true for any point you want on the parabola. All right, I think my next situation was to take some information and write an equation. So let's do that, and then we'll talk about the translated parabolas. Okay, so let's say you have a situation where you know that the vertex is at the origin, or 0, 0. And you know that the focus is 0, 3/4. And you want to come up with the equation. All right, so I like to do a quick sketch just to see what the heck's going on with this graph. I like to visualize it. Vertex is at the origin. Focus is at 0, 3/4. So that means the directrix is going to be y equals -3/4. But what else does that tell me? Well, that distance from the vertex to the focus, or the distance from the vertex to the directrix, is p, absolute value of p. That's 3/4. I can also tell, because of where the focus is located, that this is going to be a parabola that holds water. So p is positive. So p is positive 3/4. All right, so that also tells me a is bigger than 0. So then I can use my format, x squared equals 4py. I know what my p is, so x squared equals 4 times 3/4 y. So x squared equals 3y. That's my equation. Or if you'd rather, you can divide both sides by 3 and say y equals 1/3 x squared. Either one of those is correct here. And that's all they asked you to do, just write the equation for that problem. So I like to do a quick little sketch to help me visualize what's happening before I decide, what am I going to do with this? Okay. Another one of those. Shoot. I'm trying to write and it keeps scrolling. All right, so the vertex again is going to be at the origin, or 0, 0. In this one, we have a horizontal axis of symmetry. So we know that the axis of symmetry goes like that. And we know that this particular parabola goes through -4, -8. Okay, so let's try to set that one up and see what the heck that means. I'm gonna, I think, go by 2s this time. Just to save myself some space. All right, so vertex is at 0, 0. We know this thing goes through -4, -8. And then since it has that axis of symmetry, that horizontal axis of symmetry, we know that axis of symmetry is there at y equals 0. So then that means -4, +8 must be another point on that parabola. So if we're trying to graph it, we know it basically looks like that. All right. So we got to figure out what's going on as far as our focusing directrix. Okay, so this is a situation with it facing sideways. So this is a situation where you know you're dealing with y squared equals 4px. Now, since we know some of the points it goes through, we can use those to solve for p. Like, let's say I don't know, I like to use positive numbers. It's up to you, but it's not going to really matter here because the negative number, one of them will square. But anyways, so let's say we use -4, -8, the point they gave us. Well, if you plug in -8 for y, you get 64. And if you plug in -4 for x, you've got 4p times -4. So 64 equals -16p, which tells me that p equals -4. And that makes sense because this thing's facing opening to the left, so p has to be negative in that case. But it also tells me that from the vertex, I just need to go 4 units to the left to get my focus. So -4, 0. And I can go 4 units to the right to get my directrix at x equals 4. And I can write my equation, y squared equals 4 times -4 is -16x. Ultimately, I just wanted the equation. But you've also got the graph now. Yay. Okay. Expand on this a little more. Just it's not too much of a change, but let's say you don't have your vertex at 0, 0. Okay, so let's say your parabola has vertex HK still. Then you can have x minus h quantity squared equals 4p times y minus k. If you do that, you've got a vertical axis of symmetry. Your x part's being squared. So it's going to either look like this or like this. And then you can have at y minus k squared, there's your y part squared this time, equals 4p times x minus h. So if that happens, you have a horizontal axis of symmetry. So it's either going to be like this or like this, depending on whether your p is positive or negative. Of course, absolute value of p is your distance of the focus from the vertex. So really not much has changed except you're incorporating that HK in there. And it's incorporating the same way as you're used to, where your x is, you have x minus h quantities, x minus h in a quantity, and then where your y is, you have y minus k in a quantity. But otherwise, the formulas look very similar with the 4p and all. So let's say you have a situation with the vertex at -2, 3, and you're told that the focus is at -2, 2. You're asked to write the equation. Well, again, I like to do a quick sketch just to make sure I know what's happening here. It's going to go by ones again. Okay, vertex is at negative 2, 3. The focus is at negative 2, 2. So this tells me, remember the focus has to be on the inside of the cup. So this tells me that my parabola must go like this. So then that tells me that I need to use a formula with the format x minus h squared, because I need the x part squared, equals 4p times y minus k. Well, I know h and k, so I can plug in negative 2, and I can plug in 3. So that's a step forward. And honestly, I know p as well, because if I look at this distance here, straight between the vertex and the focus, I see that the absolute value of p is 1. But I also see that it's facing down, so that needs to be a negative 1 for p. So x plus 2 squared equals 4 times negative 1, which is negative 4, times y minus 3. So there it is. If you wanted to graph it a little more, you could plug in 0 for x, and you would get 2. And then you know that with that axis of symmetry, you could go 2 in the other direction and get that. So this is how your parabola is going to look. And then your lovely directrix is going to be up here. So at y equals 4. And then your vertex have been at negative 2, 3. And so there you go. So there's your equation. And your graph. All right, let's do an application problem, and then we'll wrap this up. We're going to talk about a radio telescope. Basically, it looks like a giant satellite dish. The Parkes radio telescope has a parabolic dish shape. So you have this radio telescope, and the dish has this parabolic shape. So I'm not an art major, so I'm just going to do a quick sketch of this radio telescope. Again, just kind of giving you the idea of what's happening here. And the dish has this parabola. All right. And a little bit about this. We know that, like, let's settle this parabola at 0, 0 as the vertex. And then we know that this dish has a diameter of 210 feet. So that tells me then that we could, on this grid here, we could do half of 210 and say that over here is 105, and then over here is negative 105. So then that way this full diameter is 210 feet. We also know that this distance here, the depth is 32 feet. So then we could say that we have the endpoints, these points on this parabola down on the right and on the left, have coordinates of 105 comma 32 and 105 negative 105 comma 32. So these are points on that parabola. We're curious to know the directrix on this parabola. Okay, so we have one that's right now the radio telescope is positioned in a way that we have this parabola with a vertex at 0, 0, and it's holding water. It's facing up in the upward direction. So we know then that and it's at 0, 0, so we don't need to worry about the h and k. That's gonna be okay. So we can take x squared equals 4py and work with that to help us to find this directrix. So we can just take one of the points and plug them in for x, y. So I'm going to take 105 comma 32 and plug that in. And when I do, I get p equals 86.1. So that tells me that at 86.1 units from the origin, so at my focus is going to be at 0 comma 86.1. But it also tells me that my directrix is going the other direction down here. The directrix is going to be down here at y equals negative 86.1. So there's that information. All right, then it goes a little further. What is the width of the dish 25 feet above the vertex? So straight up from the vertex, when you hit 25, so you have the dish, here's the vertex. So at 25 feet up, what is the width of the dish? So if we know y is 25, basically we need to find what x equals in order to do this. So we got x squared equals 344.5y for the equation, because earlier we knew p was 86.1, so you can multiply that with 4, and you get x squared equals 344.5y. So plug in 25 for y. When y equals 25, solve it. I'll let you solve that yourself. You get 92.8. But that tells you that this point over here is at 92.8, comma 25. But you can also get negative 92.8. So over here, negative 92.8, comma 25. So the actual diameter, just double 92.8, and you get 185.6 feet. Because 92.8 is basically the radius at that area. And there you go. So that's a practical application. All right. So that was a lot of fun with parabolas. Many of you probably have not seen like focus and directrix before. So that's so much fun. We're going to keep these kinds of concepts in mind when we look at our ellipses and look at our hyperbolas later. We're still going to be thinking along these terms of the foci, or the focus, or the foci. Foci is plural, F-O-C-I. But you're going to have some shapes that are quite different from parabola. All right, so that's it for today. Thank you for joining me, and I look forward to doing some more of this with you soon.